All right, this lecture is about absolute convergence, and basically what we're doing is taking what works for a series of positive terms and getting a little bit more out of it. So let's start with the definition. Let S be a series equal to S1 plus S2 plus S3 such that the series absolute value of S1 plus absolute value of S2 plus absolute value of S3, etc. is convergent. Then we say that S is absolutely convergent. Right off the bat, we want to show that if it is an absolutely convergent series, then it does in fact converge, okay, which is nice to know. Start out by defining a new series. We let T sub I be the absolute value of S sub I, and let T be that series T equal T1 plus T2 plus T3, etc. And let the series capital Tn be the associated sequence of partial sums. We will suppose then that Tn converges, and then show that the original unabsoluted series must converge. All right, so let epsilon greater than 0 be given. As usual, let Sn be a sequence of partial sums for S. We're going to show that S in the sequence is Cauchy. Okay. Now, since Tn, the series Tn converges, or the sequence of partial sums Tn converges, we know that it is Cauchy, and so there is an n, so that if little n and little m are bigger than that capital N, then the difference in absolute value between Tn and Tm is less than epsilon. So suppose that we do have n and m as big as this capital N. Let's look at the difference between S sub n and S sub m. In absolute values, it's equal. We assume that the m is a little smaller than the n, so that the subtraction is just snuffing off the first m terms. So we have the first m terms in absolute value, or the remainder of the terms in absolute value. The triangle inequality shows us we can separate these in absolute values, which takes us to the series T, which again was Cauchy, and we chose n and m, so this is less than epsilon. Therefore, our sequence Sn is Cauchy, it converges, therefore the series converges itself. Okay, now we're going to do kind of a technical lemma. Let phi be a permutation of the natural numbers. For every n element of the natural numbers, there is an m element of the natural numbers, so that the consecutive integers 1 through n, capital N, is contained in the set phi sub I, where I is allowed to go from 1 to m. So basically, we want to get this 1 through n in the image of phi, and so we're saying if you can take m to be fat enough, it will eventually have to contain these capital N consecutive numbers in it. Okay, our proof goes like this. Let psi be the inverse of the function phi. Then let m be the maximum value of all the psi I, where I is allowed to vary from 1 to capital N. Now, psi of I is where we let I vary from 1 to n, is contained in this, the set I equals 1 to m, because we chose m to be the maximum of all those values. Okay, and so from this, okay, I can apply phi to both sides of this subset inequality, and phi will preserve that subset. And then I'm going to apply phi to this. When I do, since they're inverses, phi and psi will just annihilate each other, leaving the set I equals 1 to n, and therefore I've got that the set I equals 1 to n is contained in phi of I equals 1 to m, and we're done. All right, so what all of this is about is that we can rearrange absolutely convergent series. So let's take S be a series that's absolutely convergent. Then any arrangement of S converges to the same value as S does. All right, and an absolutely convergent series is just as good as a series of positive terms. Let's go through the details now. Let phi be a permutation of the natural numbers, and let t sub I be equal to S of the phi sub I. So we claim that our series T equal to T1 plus T2 plus T3 converges to the same value as S. Okay. So start out, let epsilon greater than 0 be given. Since S converges absolutely, there is an n such that if n is greater than or equal to capital N, then the partial sum minus S is less than or equal to epsilon over 2. And okay, the second, okay, since it converges absolutely, again, this series of absolute converges, so this means that we can make the tail to be arbitrarily small, that this infinite sum going from n out to infinity, that's less than epsilon as well. All right. We now apply our lemma, right? There is an m such that the number, consecutive numbers 1 through capital N is a subset of this phi of 1 through phi of m. Now suppose that little n is bigger than this capital N, and let's see how close this series of partial sums is to the target value of S. We can replace, on this first equal sign, we're replacing our t's just by the permuted s's. On the second one, we're using the fact that we have these inconsecutive values of this series in here. We take the difference there, and the ones that are in here that are not in those consecutive, we put them, shunt them to the side over here. So this is still an equation. Okay, so we're just summing over the ones that are left over. Okay, now let's look at that. We take that last expression and we break it down using the triangle inequality. We have this first bit that we know we can get small. The second bit, we're adding up just a bunch of stuff that's weird and all over the place. So what we do from this step to the next, well, we clean it up a little bit by applying the triangle inequality to this big sum. And then we do an inequality again. We just say, okay, I don't know what's in here. It's salted and peppered all over the place, out beyond in. Let's just fill it in, okay? Fill it in at the price of an inequality. And so we have then the difference between S of S, this partial sum through Sn, which we chose in so that it would be small. And then we have the stuff at the end, which is the tail end of the series, which we chose n to be small there. So our rearrangement is the same value. Bam.